Hi, folks. I hope you had a fantastic weekend. We are starting a short lesson today on what we call functions. And let's go ahead and get started. So let A and B be two sets. Um, a subset of the Cartesian product is called a function if for every element of A, there's at most one ordered pair in A that has A as its first element. An equivalent definition is that if both of these are in F, um, then um, the ordered pairs are different implies that the first orders are different. That's the idea that we could not have, for example, 3, 6 and 3, 2 in here because these are different, but that is false. This would be true and this would be false, and that's not allowed. So this definition is a formal definition, and you'll see this in some places, and it's a little hard to follow, but this is what it's saying. But this is the idea. We don't want to repeat the first element of any ordered pairs. This is the equivalent of the vertical line test that you learned at some point in high school. Okay? So let's try an example. My set is only 3 elements. So what are the elements of A cross A? So I could have 0, 0, 0, 1, 0, 2. I could have 1, 0, 1, 1, 1, 2. I could have 2, 0, 2, 1, and 2, 2. So there are 9 elements total. All right, let's look at this function. F of x equals x squared plus x plus 1 mod 3. So let's look at the elements of f. So this function is the set 0. 0 squared plus 0 plus 1 is 1, so that's going to be the answer for 0. 1 squared plus 1 plus 1 is equal to 3, but 3 mod 3 is equal to 0. So 1 is going to go to 0. Let's look at 2. 2 squared plus 2 plus 1, 4 and 2 and 1 is 7. But 7 mod 3 is congruent to 1. Okay? So every first point shows up once. I have a repeating second coordinate, but that's okay. That's allowed. Okay? So let's look at the third part. Let g be the function. This should be a g, obviously. G of x is equal to x plus 2 squared mod 3. Let's list the elements for this g. Okay? So we get g of 0 is 0 plus 2 squared, which is 4. But 4 mod 3 is 1. 1 plus 2 is 3. 3 squared is 9, but 9 mod 3 is 0. And 2 plus 2 is 4. 4 squared is 16. 16 mod 3. 15 mod 3 is 0, so 16 mod 3 is 1. So that gives me 2, 1. Are these the same function? That's what this is saying. And it turns out the answer is yes, because they give me exactly the same results because we're doing this mod 3. In the real numbers, these would be different functions. But in the set A, which is only 0, 1, and 2, and we're doing our calculation mod 3, these turn out to be exactly the same function. X squared plus x plus 1 does equal to x plus 2 squared mod 3. actually say that they're congruent mod 3 instead of equal mod 3, but that's okay. All right. So let's try another example. We define S sub n to be the set of all bit strings of length n. So the only length 1 bit strings are 0 and 1, but the length 2 bit strings are 0, 0, 0, 1, 1, 0, and 1, 1. The length 3 bit strings are all of these. If I take a truth table, could I think of this truth table as a function that sends elements in S3 to elements in S1? In other words, could I think of this as a function where f of 1, 1, 1 is equal to 1, and f of 1, 1, 0 is also equal to 1, and f of 1, 0, 1 is equal to 1, but then f of 1, 0, 0 is equal to 0, and so on and so forth. Does that work? Is that actually a function? And the answer is yes. It is a function because, where did my pen go? There it goes. None of the first elements ever get repeated. And so this is the ordered pair 1, 1, 1, comma 1, 1, 1, 0, comma 1, and so on and so forth. All of these are in ordered pairs in S3 cross S1, where we never repeat the first element of any ordered pair. And so this is something maybe a little surprising. A truth table is just a table for a function, but it's a function on a set of bit strings instead of a function on a set of numbers. Okay? All right, let's look at another example. Let's say we have 2 bit strings in Sn. What we call the Hamming distance function, it returns a non-negative integer that tells the number of positions in which the 2 bit strings differ. For example, h of 1, 0, 1, 1, 0 and 0, 1, 1, 1, 0 is equal to 2, because these 2 bit strings differ in their first 2 positions, and then they're identical after that. So there are 2 positions where they differ. The Hamming distance function was first used in the early ages of digital communication. When I say the early ages, I mean the 1960s, as a way of measuring how noisy a transmission was. If the difference between the sent message and received message had a high Hamming number, there was a lot of interference. That was the idea. So let's try this part here. Find h of 1, 0, 0, 1, 0, 1, 1, 1. So they differ in the first position, they differ in the second position, they differ in the third position, but they agree in the fourth position. So the Hamming distance here is equal to 3. Okay? All right. Let's talk about the composition of 2 functions. You've done this before with numeric functions. Let's just look at this in the set theoretical sense. The composition G composed with F is a function in A cross C that contains the ordered pair AC if and only if we can find an element B that links the two, that AB is an F and BC is a G. Okay, that's exactly how it works in the numeric case. We're just looking at this in more general settings. So let's look at here. F of A to B to C. A to B is the function x squared mod 3, and B to C is just the function 2x. Okay? So, F is a set 1 goes to 1 squared, which is still 1. 2 goes to 2 squared, which is 4, but 4 mod 3 is 1. 3 squared is 9, mod 3 is 0. 4 goes to 16, but 16 mod 3 is 1. And 5 goes to 25, and 25 mod 3 is 1. So everything goes to 1 except for 3, and 3 goes to 0. G is just a function 2x, so 0 goes to 0, 1 goes to 2, and 2 goes to 4. And so G composed with F is the ordered pairs. We start with F, so 1 goes to 1, and then 1 goes to 2. So that this 1 links the 2 ordered pairs, and we start with 1 and we end up with 2. Then 2 goes to 1, but 1 goes to 2. Then 3 goes to 0, and 0 goes to 0. 4 goes to 1, and then 1 goes to 2. 5 goes to 1, and then 1 goes to 2. And so that's the, clean that up just a little bit. There we go. That's the composition from G to F, okay? So look at example 4. We're looking at a function from S8 to Z, which is a function that gives the number of 1s in the bit string X. Now this has 256 elements in it, because there are 256 possible bit strings of length 8. And so I can't write out this function. I'm not going to take the time to write out all 256 cases. But here's an example. F of 10110101 is equal to 1, 2, 3, 4, 5. So f of x gives me the number of 1s. But I want to come up with a function that gives me the number of zeros. And so what would I have to do after I have computed f of x? What would I have to do next to give me the number of zeros? So either the answer is going to be really obvious to you and jump out, or you're going to have to think about this for a moment. But if there are 5 1s, then there are 3 zeros. And since 5 plus 3 has to equal 8 digits total, then we have to be careful. Well, we don't have to be careful. We just have to recognize that this will always add up to 8. And so if I know the number of 1s, then I just take 8 minus x, and I'll get the number of zeros. And so if I calculate f, take the answer from f, and then plug it into g, then g composed with f will be a function that gives me the number of zeros in the bit string. Okay? All right. So what we'll do next time is we'll talk about a couple of terms of how we classify functions. When we can't talk about them being continuous or differentiable or things like that, we do have other ways of classifying functions, and that's what we'll look at on Wednesday. Take care.